Okay, so now let's see what happens when we have identical particles, but these particles are that they have to obey an exclusion principle, so they are fermions. Just to see what happens first, let's look at this simple example we were looking at before. So we have 4 such identical particles here, and we are filling a macrostate, and we have to look at what's the we have to pick n1 particles out of this n, which is equal to 2, and we are filling an energy hypercell, which is has degeneracy equal to 3. Okay, so in the case when we had bosons particles which are identical, indistinguishable, and not obeying an exclusion principle, I can only pick them in one way, which is this one, but then I can choose how to distribute them among the 3 available phase space cells that have the same energy. And we said just before, let me just make 1, 2, 3, 4, 5, 6. So what we said just before was, let me try to make this table proper, like this. There you go. So fine. We could put either 2 particles here, 2 there, or 2 there, or we can distribute them like this, or like that, or like that. Okay. So because the particles now have to obey the exclusion principle, they cannot live in the same state together. So this would not be acceptable. This would also not be acceptable. Let's just like that. This is not acceptable either, and this is not acceptable either. So we only have 3 possible combinations. Okay, so how we count them in general, in a general scenario? Well, you have to see that here what you have is particles and blank spaces. We can just call them x's like this. Okay, so again, it's a matter of counting permutations. So in a configuration where you have ni particles, then how many blanks do you have? Well, you have as many blanks as the degeneracy of the level minus the number of particles you have. So everything which is not a particle is a blank, and you have to consider the permutation of all of these guys. Okay, and of course, just like before, permuting blanks among themselves doesn't change the microstate. So this is just like that, and permuting the particles among themselves also doesn't change the configuration. So you can see that, of course, this goes with that, and what you're left with is the degeneracy factorial divided by this. Okay, and this you have to do for every single energy that you have to consider in the system. And what this gives you is the statistical weight of Fermi-Dirac. Okay, so this is Fermi-Dirac statistics. Okay, as opposed to Bose-Einstein statistics. Statistical weight you want. Okay, so now as usual we have to carry out the calculation, and we have to try to find what's the optimal allocation per energy of the number of particles that you have to allocate per energy level to be in equilibrium. And we just do the calculation. There's only one thing to mention here, which is, well, let's just do it. As usual, just the logarithm of the Fermi-Dirac. I'm going to make already the Stirling's approximation, and I'm going to assume that this degeneracy of each energy level is huge, which is very safe approximation to do if you have a system of a lot of particles. Okay, that is certainly going to happen. So what you have here is the sum over the energies. The product turns into a sum, and then here you get the degeneracy times the logarithm g epsilon I minus 1. Then the denominator, you get the ni logarithm of ni minus 1, and you also get minus, and then there is this g ei minus ni, the logarithm of g ei minus ni minus 1. Okay, that's just Stirling's formula right here. And like I said, I'm assuming that the degeneracy is large, I'm assuming that n is large, but I'm implicitly also assuming that g is a lot larger than n, because still g minus n is very large, and I can apply Stirling's approximation. So if you want me to write what the assumption is that this is not just large, this is much larger than this, which itself is large. So that this difference is large. Okay? So in principle this is just a guess, okay? There is nothing that I can say to justify this now other than we will arrive to the correct result just by assuming this, okay? So let's just see where we arrive. But actually let me write here what we have to do. As usual, we'd have to maximize this thing subject to constraints, okay? And these constraints are going to be, well, the number of particles is going to remain constant. There is some multiplier here like this, and then also a second Lagrange multiplier saying that the energy is another constraint of our optimization, has to remain constant like this. So this whole thing has to be equal to 0. What do we have? Okay, so from this logarithm of the statistical weight, what we get is sum over all the states of here it is d and I, so the variation, the infinitesimal variation and I, and then the minus logarithm of ni. We also get a -1 term that comes from the other derivative of the first term, a +1 that comes from here, and then we get plus logarithm of g ei minus ni that comes from this term, multiplying that. But we also get another -1 from here and another -1 from there. Okay, and then we get a minus gamma, and then we get the usual minus beta epsilon 1. Okay, the whole thing equals to 0. That goes with that, and we want to collect all the little constants that are like this. So this in this case is the gamma plus 2, but this is just an arbitrary thing because this is an arbitrary thing. So we are going to call the whole thing minus alpha. Okay, just like we did before. Before it was gamma plus 1, now it's gamma plus 2, but it doesn't matter. So what we have is that the bracket has to be equal to 0 because this variation is arbitrary. And what this tells us is that this thing minus ni divided by ni equals alpha plus beta ei. Okay, then you exponentiate and you get to this. Okay, and I'm going to take that to the other side, so it's e alpha then e beta epsilon I plus 1. So when you invert this, you find that the equilibrium occupation in this case is going to be the degeneracy as usual and divided to by e alpha beta epsilon I plus 1. Okay, so this is the key difference. Okay, so now we have plus 1 in this Fermi-Dirac statistics. And in the case of the Bose-Einstein, we had a -1. Okay, so this is Fermi-Dirac. In the case of Bose-Einstein, we had similar thing, but with a crucial difference, which is this minus sign. So the behavior is completely different. This is Bose-Einstein. And remember what happened. If the particles are identical but distinguishable, well, you don't have neither plus or minus, you just have this. What we found in the previous, well, in the first video of this lecture. And this is the Maxwell-Boltzmann, okay? Which is classical in a way. Okay, so that's a kind of summary table. In this lecture, which is really an extension of the previous one. So we are not going to apply this to anything, but just knowing these things, knowing the equilibrium occupations, knowing the statistics of the different types of particles, you can solve many problems. And you get very different results if you are working with bosons or if you are working with fermions. And one comment to make here is that you can recover the classical limit directly from either the Fermi-Dirac or the Bose-Einstein case. Okay, so what you need to do, well, clearly mathematically, right, if you just look at this, you have to find that this exponentials, or rather this exponential, has to be a lot larger than 1. Because if this is the case, well, you don't care if you add 1 or if you subtract 1. It's roughly the same thing as not doing anything, right? And let's just see what it means for this to be very large. So what we have is that Ni divided by Gi, okay, so I'm just dividing by this. I want that thing to be very small, okay, and that thing is going to be 1 over a very large number plus or minus 1. I just want that thing, which is the inverse of a very large thing, to be very small. And essentially, when this is very small, I can approximate that by e to the minus alpha, e to the minus beta epsilon I. That's what I'm saying. So what I'm saying is that when this exponential is huge, I don't care whether I add or subtract 1, I just get roughly the same thing. And this thing being small is what I interpret as being the low density limit. Okay? So if I have, I have a lot of particles per energy, that's right, but the number, or like the degeneracy of each energy level is so huge compared to that, even if this n itself is a large number compared to 1, it's nothing compared to all the available energy states that would have that same energy, in that degenerate subspace. So, okay, that's low density limit is interpreted as some sort of classical limit of either the Bose-Einstein or the Fermi-Dirac distributions, okay? So when you have a lot of very high density, you say you are deeply in the quantum regime, and when you have low density, you are in the classical case, okay? So that's just the only thing to consider. Now, the next self-study pack, it's really optional, because there's no assessment linked to it, but I do recommend you to go through it. So this is Planck's law and the free electron model. Essentially, it's just applying this formula to the problem of black body radiation and arriving to Planck's radiation law, which is central result, and that also ignited quantum mechanics on its own. And then the Fermi-Dirac distribution to apply to study the free electron model, which you can successfully use to model any metals. No? I discuss things that you have probably already seen in condensed matter physics, but from a different perspective perhaps. It's very short. I would recommend you to look at it. But, if you are too busy, you may defer reading this to when you are not so busy anymore. Okay, so this concludes the entire module, at least the asynchronous part. We still have a synchronous session left in the last week, when we are going to go over some exercises on partition function, which are actually quite important. So I very much recommend you to either attend to that last synchronous session or at least to watch it on recap, because it contains some important examinable contents. Okay, so I will then see you then.